Today I am going to explain the designing of an half adder and a full adder. Before going into the circuit, let us first understand what an adder is. An adder is a combinational logical circuit used to perform a binary addition. Since computer works with binary numbers, so adders are very important building blocks in digital systems. So they are used in calculators, processors, counters and arithmetic logical units. First, let us discuss the half adder. What is an half adder? Half adder is a combinational logical circuit. It adds a single bit binary numbers. It adds two single bit binary numbers. The two input bits are represented as A and B. And the output is called, the outputs are, and the two outputs are sum and carry. This is a basic large diagram of half adder. The sum output represents the result of adding two inputs A and B, and the carry output represents the carry generated during the additions. Half adder is called a half adder because it can add only two input bits, and then it does not have any provision for accepting a carry input from a previous stage. Next, before designing the circuit, let us recall the basic rule of the binary addition. When we add zeros and 0, the result will be 0. When we add 0 and 1, the result is 1. When we add 1 and 0, the result is 1. When we add 1 and 1, the result is binary 10. Binary 10. Here 0 is taken as sum and 1 is taken as carry. Okay. Now let's construct the truth table of the half adder. For a two input variables A and B, we have four possible input combination. When A is 0, B is 0, both sum and carry is 0. When A is 0, B is 1, the sum is 1 and the carry is 0. When A is 1, B is 0, the sum is 1 and the carry is 0. And then both A and B is 1 and the sum is 0, the carry is 1. Using observe the sum column. Both the inputs are different, then the sum is 1. Sum is 1. Then the sum is behave like a XOR gate. Sum is behave like a XOR gate. The sum is obtained using a XOR gate. Next, observe the carry column. Both the inputs are same. The carry is 1. It behaves like a AND gate. So the carry is obtained using a AND gate. Next, using a K-map, we can get an expression. First, for a K-map for sum. Take a two variable A and B. Here 0, 1 and then 0, 1. Here 0 is B bar, 1 is B, 0 is A bar, 1 is A. First 0, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 0. Okay. And then we separately taken a 1. Here 1 is A bar B and here 1 is A B bar. Now we add this. Then it is A bar B plus A B bar. Then the value of the sum is A XOR B. Similarly, we do a K-map for carry. Take a variable, two variables A and B as an input. 0, 1, here also 0, 1, here 0 is a B bar, 1 is a B, 0 is a bar and 1 is a A. 0, 0, 0, 0, 1 is also 0, 1, 0 is also a 0, 1, 1 we taken as a 1. Here, then it will be a and B. So the carry value is A and B. A and B. Now let us design the half adder circuit. First, the input A and B are connected to an XOR gate. The output of the XOR gate gives the sum. And then similarly connect the input A and B are connected to the AND gate. The output of the AND gate give the carry, value of the carry A dot B, A and B. And then limitation of an half adder. The main limitation of an half adder is that it cannot accept the carry input. When we add multiple bit binary numbers, a carry may be generated from a previous column. The half adder cannot include the previous carry for the addition. To solve the problem, we use a full adder. Next, let us discuss about the full adder. What is a full adder? Full adder is a combinational logical circuit that adds 3 single bit binary numbers. The 3 inputs are A, B and C in. The carry input is usually written as C in. The carry input represents the carry received from a previous lower order bit. Full adder produces 2 outputs. The outputs are sum and carry out. Unlike a half adder, a full adder can handle the carry generated from a previous stage. Therefore, full adder are used for adding multi-bit binary numbers. Since full adder has 3 inputs, it has 8 possible combinations. Let us understand this truth table. When all the 3 inputs are 0, sum and carry outputs are 0. When any one inputs are 1, then sum is 1 and carry out is 0. When any 2 inputs are 1, then sum is 0 and carry out is 1. When all the 3 inputs are 1, the decimal total is 3. The binary representation of decimal 3 is 11. Therefore, the sum become 1 and the carry out become 1. Now, using K-map, we generate the expression. Now, let us observe the sum column. The sum is 1 when all numbers of inputs are 1. Here, take a 3 input variables A, B, C in. 0, 0, 0, 1, 1, 1, 1, 0, 0. Here take 0 and 1. Based on a K-map, possible of diagonal mapping. But here considering individual mapping. So here A bar, B bar C in and A bar, B C in bar and A, B bar C in bar and A, B C in. Here and then we reduce the equation into A bar, B bar C in plus B C in plus A, B bar C in bar plus B C in, and then we can return as A bar, B XOR C in plus B X not C in, and then again we return as A bar, B XOR C in plus A, B bar XOR C in bar. Then finally, therefore, the sum can be obtained by applying the XOR operation to A XOR B XOR C in. C in is nothing but carry input. The sum output is written as sum is equal to A XOR B XOR carry input. Similarly, using K-map for carry, let us observe the carry out column. The carry out become 1 when at least 2 of the 3 inputs are 1. Here also take a 3 input variables A, B, B in. Here 0, 0, 0, 1, 1, 1, 1, 0 and here 0 and 1. Okay. Based on a K-map rule, we pair A bar, B bar C in and here pair A bar, B C in and then A, B C in. And then pair A, B bar C in and A, B C in. And A, B C in and A, B C in bar is another pair. The carry out is equal to A, B plus B carry input plus A carry input. In this expression, multiplication represent the AND gate and plus represent the OR gate. By using this expression, we can design circuits. Here, consider 3 input variables A, B, C in. A XOR B. Take a 3 input variable A, B, C and connected through the XOR gate. And the output of the XOR gate is the value of the sum. Sum is equal to A XOR B XOR C in. And then connect for a carry, connect A and B in an AND gate. And then connect B, C in another AND gate. And then connect A input and C input in an AND gate. The output of the 3 AND gates are connected to the OR gate. The output of the OR gate is C out. The C out value is equal to BC in plus AC in plus AB. Next, design a full adder using 2 half adder. Full adder can be designed using 2 half adders and 1 OR gate. Let us understand the design step by step. First, A and B are given as an input to the first half adder. The first half adder produces an intermediate sum and the intermediate carry. The intermediate sum S1 is obtained by performing an A XOR B, and then intermediate carry is obtained by performing A and B. Then next, the intermediate sum S1 and the carry inputs are given to the intermediate carry sum S1 and the carry input is given to the second half adder. The second half adder produces the final sum and the another carry. Let us call the second carry is C2. The second carry C2 is obtained by performing S1 and Cin. Here we represent S1 as A XOR B to Cin. The final sum is performed by obtained by performing an S1 XOR Cin. Here S1 is represented as A XOR B XOR Cin. Now we have two carries C1 and C2. This C1 and C2 are connected to the OR gate. Then final output C out will be C out is A dot B A XOR B Cin plus AB. The final outputs of S is A XOR B XOR Cin, and the final carry out is A XOR B Cin plus AB. Finally, the full adder can be designed using 2 XOR gates, 2 AND gates and 1 OR gates. And then next, let us compare the half adder and full adder. Half adder has a 2 single bit binary inputs, that is A and B. Full adder has 3 single bit binary inputs, that is A, B and C in. Half adder and full adder produce 2 outputs, sum and carry. Half adder cannot accept a carry from a previous stage, but full adder accept the carry from a previous stage. Half adder use only 1 XOR gate and 1 AND gate, but in full adder 2 half adders and 1 OR gates are used. Half adder is mainly used in a least significant bit. Full adder used in a remaining bit position of a multi-bit binary adders. Applications. Half adder and full adder are used in arithmetic logical units. They are used in calculators and digital processors. They are used to design parallel adders. They are used in calculators and then digital signal processing systems, counters, multipliers, etc. Thank you.